is the context switching by the time sharing. So let's say that there are two processes accessing the serial port. If P0 currently requests to read the data or send the data or receive the data for this port, then this one may not use. So to use this one, keep checking whether this is available or not. How to check? Using the status check, status register. So if status register is 1, is currently available. If otherwise 0, it is being used by another. So this process 1 cannot use until the P0 is the current process is done. Once current process is done, the status bit is changed to the 1, and finally P1 is activated. This is the step. The using based on the polling. Problem? Busy waiting. So this one, P1, keep checking. When you check the status, it requires at least 3 instruction. You need to read the register information like read the status and check the status bit, and based on that status bit, the branch. If 1, the use. If otherwise, the wait. And the next, keep waiting. So this busy waiting actually consumes the CPU resource because every time it needs at least 3 instruction cycle. So these the two address such a problem. We already discussed about the interrupt based. The interrupt based instead of keep knocking. Okay, so we start the interrupt the entire operating system. Then I'm ready or I need to use such a device that is interrupt based approach. So we have talked about such an interrupt based approach in the chapter 1 and 2. Then each interrupt, like I'm using the disk serial or the disk drive. So each one has each interrupt. There are different types of interrupt. Okay, so for each interrupt signal, so we CPU define such a number which is called the interrupt factor number. So you can see the 0 is divided by 0. Okay, divide error, which is critical in computer system. Computer system is a discrete, so divide by 0, no way to handle. It's a 0, 0, 0, 0. It's an infinity number, so it's the first, the interrupt. And the 1 is the debug, and so on. So for each the vector, we need whenever this interrupt means it's a stop, then the CPU need to do something, right? So for example, the divide by 0, we need to stop such an operation. So or if any step forward, so we need to display, start the current instruction and display the current status, and so on. Or in case of page forward, so we will discuss today or maybe after Thanksgiving. In case of page forward, we need to find the free page from the memory. So we should do something. Think about the exception handling in the program language. Try and catch. And you need to do something. In case something happens, check the condition and do something. So this is called the trap. So trap actually same mechanism, same idea of the interrupt. So because of that, we call such an interrupt as the software interrupt, which is the trap. So same thing. In case this one is happen, we need to do something that is called the interrupt handler. So interrupt handler means it's the function or something to do. It's a pre-program, the hardware embedded program on your memory. So each the vector number point to the address of your memory. The memory area is a map. So 0, 0, 0, and the map. So in case of divide by 0 and do something, it's a pre-coded. It's a kind of function. So this the program the interrupt handler will be executed. Where is that? Executed. So that is the interrupt handler will be executed for each interrupt. So we are not going to discuss the details of that. That is from now on it is going to be hardware level. But the operating system, the support at least such an interrupt. Then they should be able to use such an interrupt the vector and the interrupt handler. Okay. So this slide shows the interrupt-driven I/O cycle. That's the exactly same that we discussed. Okay, and so the software interrupt is the same mechanism. So that is called the exception or the trap. Okay. Then another I/O is the general I/O is like this. There is an instruction to read the data, load or the store I/O. Then it's a byte by byte. So this control either the polling or the interface, then let's say the interrupt, then the write the use the memory map the I/O. So this the memory space will be used for the I/O. Then read the data from the hard disk drive. Then the such a data A will be stored at the here. Then the CPU read the data from here. Then find next instruction, next instruction. So for each byte, how many instructions? So at least one or two the instruction. Or in case of the polling based I/O, you need 3 or more instructions are needed for each byte. So really expensive. Really the waste of the CPU space. In case we like to think about the video. Video is 1 gigabyte or 2 gigabyte. It's a stream. So if you think about the file related object used in the Java or the Python, it's a file stream. So reason is that it's nothing but the sequence of a byte. So if we read the video file, a lot of instructions are needed. But they are just the same routine of the instruction, right? So instead, why don't we bypass such a CPU? That's right. Because anyway, we are going to read such a 1 gigabyte the byte string. So instead of using the CPU the instruction, once it is started, directly put the memory. Directly put the byte, next byte to the memory, and CPU just to read. Okay, so this is called the direct memory access. Nowadays, most of the CPU the support such a direct memory access. So direct memory access is a DMA is a hardware. So we need to specialize the hardware, which is also require the controller, DMA controller. So this device is connected to the DMA controller. And let's take a look at this one. So first, the CPU need to read the data from here. The typical way is for each byte, each instruction will be executed and load the data into the memory. Instead, if we read the data through the DMA, once it is started and the DMA controller actually the interrupt, then bypass the CPU instead of just using the bus, the load byte by byte until the end of the file to the memory. So, but this time, this requires hardware. So sometime, all time, not sometime, all the operating system, if you enter the BIOS program, so you are able to select whether you are going to use the DMA or non-DMA. Okay? But nowadays, all of the hardware they actually use the general purpose, the CPU use such a the DMA approach. So much faster. So this is the direct memory access. And also to support such I/O, so there are application level I/O and kernel level I/O. Kernel level I/O means operating system provide the I/O related the component. On the other hand, the application level is you can actually project the application program like the file, including file system, and the specialized file system. So that is the application level I/O. There are different types of I/O that we can imagine. We already have seen or discussed, like the sequential and the random access. We have seen in the tape or using address, we can do the random access. Synchronous, asynchronous means synchronous. When you read the data, you check the return of the request. So once the CPU confirm, then read the next one. That is the synchronous. On the other hand, asynchronous is regardless of so sometimes it may be failed, something happens, the disk controller cannot return the data, but keep reading the data. And later, using the parity check or the status check, if there are any missing data, request again. So that is asynchronous. And so this kind of I/O can be supported by the operating system level. That is called the kernel I/O structure, which means we are able to use the system library to support such a thing. So most common I/O related system library is the IOCTL. So if you go to the main page, so you can check the system library related to the I/O. So using, for example, if I want to develop the library or the C program or the Python program to control the specific device or the new device program, you can use IOCTL, the system library. Okay? At that time, you can specify whether this is asynchronous or the synchronous, and so on. Depending on the I/O device, there are different types of the I/O, like for example, the CD-ROM is read-only, like that. I think that you guys can understand the characteristic of the I/O device you already use. There are more commands to read and write the data. So think about your microcontroller class or the computer engineering class. In your microcontroller class so you develop the program to use the mouse. Okay. At that time, what you guys need to do is first what types of I/O you are using, whether this is a USB or CD-ROM, and then each hardware has the specification. Like the number 0 pin used for status check, number 2 is the input data, and number 3 is the output data. Then after that, you guys can use the IOCTL or the related system library to control such an I/O device. So that is what you guys doing to develop the I/O the program. Okay. For the network device, so like the network file system, you can use the network protocol like the TCP/IP based socket. That on top of that is the same as the network. Another the I/O device is clock and timer. So clock and timer also is considered as the I/O device. How that anyone who ever change the battery of your computer, personal computer or laptop, anyone? Nowadays, I don't think. Usually the battery life is longer than the laptop. So may not, but I did a couple of times. Sometimes if you change it, or if you run out of your battery, oh, by the way, that battery is different from the laptop battery. So in the motherboard, so even though you do not have the battery power for your general purpose, so we need to keep the current time. Okay, so to keep the current time, there is the battery inside, but that's also battery. It will be run out of eventually. So if you replace such a thing, the time usually reset as current time, unless you connect to the network. That is the network NTS, network time, NTP, network time protocol. But if you do not connect, it will be set as 1970 January 1st, 00001. Do you remember the family tree of the Unix system? It starts from 1970. Usually, the year time is reset to the 1970 January 1st. Okay, so such a time and the clock. So operating system needs such a time for what? Just general time, like the current time is 10, something like that. Also, CPU time for journaling or something accounting purpose. So CPU time. So and also it can be used for the context switch, the CPU scheduling, and not only CPU scheduling, I/O device scheduling. It can be used for the many others. So the operating system used such a time from the hardware as an I/O. So if you need to read the time, it's exactly same as the reading the data from hard disk drive. You can actually load the specific area, the address of the memory on your processor, then read the data. It's also based on the IOCTR. You can use the IOCTR system library to read and write read the data. Okay. Their resolution is 1/60, but sometimes it's much the high precision, but it's a programming level. Okay, so it is usually but nowadays it's higher and higher. And also, if your system is connected, it uses a network. So I think the network time protocol NTP, so you can automatically update your current time. So we don't have to reset. So we talk about this synchronous, asynchronous, and vector. The I/O is as the name implies vector. So we can if we do not read the data only one. So what about the batch of the I/O? At the time we can use such a vectored I/O. Okay. So if we can use the multiple. We can use a multiple buffer to read the data. That is the vectored I/O. Okay. To support another component of such a kernel I/O system is the scheduling. We already talked about such a scheduling, and the buffering we did. So also we talked about last time the double buffering. The one is from the memory, and another one is the other I/O device. So sometimes it's the double buffering, so we have the unified buffer. So buffer means, oh by the way, what is the main difference between buffer and cache? It's different. We have the cache and the buffer.
Cache is always a copy of something, and a buffer can have anything, essentially.
So if you drive the highway, so when you exit, so you need to use the ramp, and usually you can see the buffer in case accident. If you hit the ramp, and the buffer means usually in between
Extra space.
high speed and the lower speed, high bandwidth and the lower bandwidth. To reduce the gap of the speed or bandwidth, we can put the buffer, like the buffering. Like if you think about the long, probably you may not refer to such a thing. So when I use the internet first time, it's very tough to watch a video, especially live streaming. So at that time, usually suggestion is increase the buffer. So we can use the buffer. It's not real time. We can keep the incoming data in the buffer, then the out. Then we may not realize such a gap. Cache is the reuse. So for the fast media and the low speed media, then we can put the frequently use data in the fast the media. Usually fast speed the media is much more expensive. Okay? We cannot have the same size as the lower speed the media, so we can put the frequently accessed data to the cache. So cache and the buffers, sometimes we use interchangeably and mixed, but the main concepts are slightly different. So buffer is in between the high speed and the lower speed, and it's a media. Then we can keep the lower speed the data to serve for the high speed media. On the other hand, the cache is a copy of frequently accessed data from the lower speed. Then put the frequently accessed data to the high speed, the media. So that is also supported by the cache. So most of the time the cache should be managed. The more important thing in the operating system is how to keep the cache data. So mostly frequently used one is LRU algorithm. Least recently used algorithm is a kind of a linked list based on when it is accessed. So we will talk about the LRU algorithm in the memory management. So the memory device is used for both the cache and especially cache a lot. So we will see such an algorithm. Spring is another one. So we have seen the short-term scheduling, long-term scheduling. So long-term scheduling is usually when we cannot divide the job, so we can do once it is started, it will be completed. It's long-term scheduling. For the long-term scheduling, so pooling can be used like the printer. So nowadays only printer use such as pooling. So we cannot stop in the middle of printing, right? Once printing job is started, it will be completed unless we cancel it. So that is a spooling and so on. So I'm going to, so this is an example of the Unix IO kernel structure. As we discussed in the file system, interface file system, the implementation, the file system has the memory structure. So for the memory structure, that the file are managed by per process in the memory. So which means one process which files are accessed. And also system-wide in the kernel operating system, for each file, which process are accessing the file. So that is the supported, that should be supported by your operating system. Okay. It's not critical, but nowadays it's more important how to manage the file for I/O devices. Specifically, the portable, the operating system like the Android or the iOS. So there the power management is more critical. Okay, so like the Android, they are better and better, but still somebody say if you actually somebody says it's not probably only way, but the best way to be a billionaire. I think who is the richest one? The YouTuber? In the morning, I read the article. Bloomberg donate the money to all the university.
Oh, yeah,
1.8 billion
to Johns Hopkins.
Yeah, Johns Hopkins. So think about the Johns Hopkins for your future graduate school.
Medical school.
He just said his money can be used for the student loan. So like that. But anyway, so best way to make the money nowadays is the battery. So if you can make the battery is the kind of 30% increase the capacity, probably you will be super rich. Like the car industry, so it's changing to the electric car. That totally depends on the battery power. And also, I think the idea of Elon Musk is he spread out the battery. Instead, the conventional way, the shape of the battery is like the box. But he spread out such a battery so to the car. So, and the cell phone, definitely if you travel to the China, you can see the most of people hold the external battery. Nowadays, even we can see a lot of people find the power outlet in the airport and so on. So battery is I think really the possible way to be a billionaire. But in the operating system, right, there are a lot of ways to save the power. So but the demand is like the multitasking and more of the multitasking. So frankly, I understand why the Apple did the change of the power usage in the old version of iPhone. They actually block some of the functionality to save the power, to avoid any waste of power. But because of that, it was actually the record. Something happened. So that is the power. So I'm not going to explain the example of the stream. Then move back to the chapter 8. For those who were late, so we have final exam December 10th, which is assigned. The schedule, I cannot change it, but fortunately we have exam from the 10:45 a.m., which is reasonable, to the 12:45. So coverage will be after the midterm, chapter 7, and including 8 and 9, and 10 through the 13. So it's not comprehensive, so you don't have to study the midterm exam again. Then we have the due of the project 2, which is the November 30, and also those who got the 0 mark for the project 1. So Gidok, did you announce the details of the second chance of the project 1?
Oh, I just create the.
Okay, why don't you send a reminder email what they need to and how you are going to grade. So please, this is the second chance for those who didn't do a lot for the project 1. So why don't you do the second chance of the project 1? Mostly it's copied. Okay, so what is this? In your microcontroller, what is the name, the course number of the microcontroller class at UB? 268? 267?
Microprocessor?
Yeah, microprocessor.
286.
286.
Yeah.
So you probably learned the assembly code, like this one.
Yes.
One of my regret is I didn't take any computer engineering class. Definitely my undergraduate is mathematics, so I didn't have a chance. I had a chance to take the couple of programming class, but never ever. And even the graduate, so I tried to take only the computer science related course. So, and I study myself the assembly code. So, but I strongly suggest to you guys, if you didn't have a chance to learn the assembly or the microprocessor and microcontroller, so embedded the system, please do that. And this is I surprised that some of the students never ever seen such a assembly code. So this is one of the most popular instruction code move. So somebody says roughly the half of the assembly code is a move. Yeah, that makes sense because sometimes we need to move the data from register to register, or mostly memory to register, and also register to the memory, and also memory to memory. So at that time we can use the move. Another popular the instruction is load and store, like this. So this instruction, this is operation code, is defined by the chip, the manufacturer, like the ARM, the AMD, or Intel, they or the 86, 88, so they define their own assembly code. It's not many, so usually 70, 60, 70 mostly. So some of the microprocessor, so like the for the microcontroller, they have the very last and also there's a mode, and so sometimes we need a 2 byte of the data for this. Then typically this is the cycle of the execution for the instruction. So we need to get the instruction code and the decode, like the from here. So what's the operation code of using the first 6 byte bit? So it will be moved, and that's so on. Then sometimes it has the operand, the argument. So we need to fetch such an operand. So it depends on the instruction. Some of them are needed, some of them are not. And then finally execute, okay? And store the result in the memory. Or if doesn't need any operand, the fetch and the decode, read, and the execution. Then sometimes you need one cycle of the CPU, one CPU cycle. Sometimes you need 2 cycles. Some of the complicated, complex instruction need 3 or 4. So when you purchase the computer system, especially the CPU, so usually we are looking for the high gigahertz, like the currently 5 point something, or the 3 point, at least the 3 point something gigahertz. What does that mean, gigahertz? It's a giga time, the frequency. It's a cycle. Okay?
It's
It's a gigahertz. Then sometimes you need the 2 cycles to process one instruction code. Sometimes 1, sometimes 4. So you need to check average cycle per instruction. If that is high, so like the 2 and the 1.5 is totally different. It's a huge difference. So you need to actually check the average, which is not easy to find from the box. So you can check the specification. So using this one, so we can actually get process the instruction. Then one more time. So this is our memory. So mostly this lower address is used for the operating system, your kernel. And the process will be loaded into the memory. This is the process. Then this is actually as we discussed a lot, has a very specific data structure. So the programming code, the instructions are in the text area. So this CPU has the program counter, the register. Using program counter, you can go to the location. Actually, there's another one we need to consider based on I will set aside. We will discuss later. But once we know the location of the first instruction, and we can follow this step as discussing here. So using the move, we can bring this one into our CPU register, and execute it, and the result will be stored at your register, sometimes moving back to your memory. Okay, so at the time we use definitely they are connected to the bus. What about another process? Another process will be loaded into the memory and the number of, unless this is a single processor the operating system like the MS-DOS, so we can have multiple processes. What can be the problem of this one? What can be the problem? Using the memory to execute the process, to run the program. So this is a very basic the execution cycle for each instruction based on the process, the structure. What can be if you develop the operating system, what will be the critical issue to use them? First, what is a memory, by the way? Memory is, so what are they? It's an address. It's a storage organized by just the address. If you know the address, you can read the data. It's like the open field. Can you see if you go to the middle of nowhere, so sometimes you can see the fence, but sometimes not. But it's divided by each owner, but you don't know clearly. So if you have the GPS, you can go, but sometimes it's a private area, right? Then it will be a problem. Same thing. It's just the sequence of address. If you know the address, you can go anywhere. It's not actually blocked. There's no fence on the memory. So unlike this one, or unlike the hard disk drive has the sector number and or even other the disk. But memory is not. It's a logical concept. It's a sequence of the address. So you are able to, if you know the address, you are able to go to anywhere. So which means it can be huge problem. If something happened, the program counter point another process, and if you write the data in the middle, it will be the crash. So this problem is called the memory protection. So memory protection is the first issue. So how to protect the memory structure, how to protect the process. Okay, that is the first problem in the memory management. Second problem is anyway, this is the hard disk drive and this is the memory. Why do we, according to the von Neumann architecture, why do we need the memory?
It's crucial to everything that we do in terms of that architecture.
Why we thought, the von Neumann, why he proposed such an architecture? The main idea of the von Neumann computing architecture is a memory. So CPU can access the data from the memory and they are connected through the bus. Then why? Because this one is huge. This one is small, but this one is faster. Much faster than this. So CPU can access the data only here. If we need to access the data here, so CPU cannot process, cannot get the full benefit of the processing. So this one is faster, but problem is smaller. So utilization. So always when we develop the operating system, when we consider the operating system, such a managing the memory is crucial in terms of what? Performance. So if we think about the laptop is slow, my computer is slow. First you guys can do is increasing memory size. So you can replace your memory card, you replace your physical memory. So, or if you cannot change it, or if you cannot replace, you actually remove, starting process. What does that mean? Starting process means it will be loaded into the memory. Your memory will be occupied as a default. So you can try to increase the utilization of the memory or free up more memory. So memory is really crucial for the performance. So these two, how to protect the memory data and process, and how to use the how to keep the utilization in the memory. So we are going to talk about these two mainly in the chapter 8 and chapter 9. So first, chapter 8, we are going to talk about the memory management entire of this one. Okay. Then second thing, so main memory is not big enough. We are going to think about virtual the memory management. So virtual memory means it's not real memory, it's a virtual memory. So have you ever heard about the swap operation? Yes. In the synchronization. So we can use the swap instruction to lock and unlock. So if you remember, what is a swap? Swap is exchange. So one of the old naive idea of such a utilization is if we do not have enough memory to load to create the process, we can swap this one and the other. At that time, the process is back to the virtual memory space. So actually, the swap is a really expensive operation. Nowadays, we don't use the swap operation. Instead, swap can be used for name of virtual memory. Then, what is a really virtual memory? So we are going to consider who is the consumer of who used the memory space. CPU and also for what? Process. So we consider process, your program, as a part of the memory always. It doesn't matter whether this is the physical memory or not. Okay? So we will talk about what's the idea. But we will extend the data structure into the virtual memory. Then to do that, instead of using the entire process structures too big, we are going to divide. Fix the size of the data structure, which is called the page. Have you ever heard about the page? What paging, page fault, and so on? So one of the easiest way to measure the operating system computer performance is check the number of page fault. Okay, so it's still being used, and it's a good indicator to judge whether my system is good performance or bad performance. The page fault is instead of swapping, replace the entire process, the small unit. Let's think about the file system. File system, this is the sector and the track number and so on. Eventually we create the block. So block is the I/O, the unit. So 512 byte, like this. And this page is the memory I/O unit. So instead of the process by process replacement swap, we are going to use page by page swap. It's a page replacement. Then at that time, number of page fault, number of replacement actually indicator of your performance. Less page fault. You cannot avoid such the page fault. You may have the page fault, but you can reduce. If you can reduce the number of page fault, your system will be better performance. So the chapter 7, chapter 8 and 9, we will talk about mainly the main memory management and the virtual memory management and the page replacement. So these are the general topic that we are going to discuss. Then, first one, how to protect the process. Idea is very simple. So, when process is running, the CPU has the number of the register. Register is the storage. You can keep the data, or you can keep the instruction. Also, you can keep the other information like the PC. which is the popular, the register is the program counter, is the address of the next instruction. And however, this for example, program counter is 1000. This 1000, address 1000 means it's not actually physical address. Each program, when after compile, so program counter is starting from the 0, and this is a total size is 2000. Then 1000 is here. So if we load this process into here, like this is F, the 0, 0, like the A, 0, 0, 0, 0. Then this one will be loaded into here, so this one will be B, 0, 0, 0. Okay? Or if the process loaded into other place, this address will be changed. This is a relative address, not absolute address. Okay? So, to decide once this one is loaded into the memory, then we are going to keep the two parts. Where is the starting address, which is called the base address. So base is here. Another one is the size. Size is the limit. So limit address is the maximum of your process. So in this case, 2 dot. So 2 registers are used to protect. We cannot actually make the really physical fence of the process. Instead, we will keep the 2 more the address in the register. One is the base. Base is the starting. Okay. Limit is the size of that. Okay. So which means whenever we have the address program counter, check. So whether this address is bigger than base. Okay. Bigger than base and less than base plus limit, which means the highest memory address is the size. So whether this program counter is less than this. So always it will be in between. This is the base and this is the base plus the limit. So this one is always in between here. So then if out of such a range, it will be the trap or the inter. It's out of the space to protect the memory space. So it cannot be the out of the base and the base plus limit, always in between. Okay? For each instruction. So for each instruction, we need to check. The first reason we cannot have the absolute address of that. There were a long time ago. So when we have the MS-DOS, the single processor operating system. So always the one process will be loaded on top of the operating system, which means only one process, single process is always the same starting address. At the time, we can have the absolute address. However, when we have the process operating system, the multitasking, we don't know where it goes. So it has only relative address. So because of that, so we are going to keep when we start the program, when we start the process, when we execute the program, the base and the base limit is actually determined by the size of the process. So then, question: where can we keep such a base and the limit? Where do we have? Eventually, it will be loaded into the register, base register, limit register. But if this is not in the active, like for example, ready queue, then how can we keep such a base and limit, even including program counter? we can keep such information in the PCB, process control block. So process control block, keep the, do you remember the context switch means the one PCB and another PCB. So we back up the current processor PCB including register information, which means so we keep the such a register information including base, limit, and program counter into the at the PCB. And the next process PCB will be loaded. Loaded means all the PCB and copy to the register. So we can keep the when we start the process, then we will determine the limit, and the base will be the assigned when we execute, when we start the process. So that is the base and limit. So using such a base and limit, so we can keep we can protect the process. This is not the programming level, it's a hardware level. Your CPU chip should provide such the protection functionality as a hardware chip. Okay? Otherwise, if we implement this one in the software like the operating system level, it's really overhead. For each instruction, we need to do this one, the comparison and the branch to the error. If out of then if yes, then finally CPU can access the data from the memory. Okay. So at the time, such a address, the relative address will be changed to the physical address, which is called the binding. So we need to bind the address from relative to absolute. Okay. So for better understanding, this is the process when we compile and the link and load and finally execute the process. So starting from the source program, like a.zip file. So if we have the source file, first we need to compile. Okay. So this compile is the executable file. It's a sequence of the instruction, but their address is a relative address. Okay, we do not know exact address. It can be here, it can be here, it can be here, depending on the execution. So it has only the relative address. Then we have the object module has the relative address. So linker actually combine number of objects. So this is your source code, but we need other shared library and so on. So other object file. By combining, so that is by combining number of objects, so we can link. Then the next module is load. Load means move this one. So this is our source code plus link. The link is other object. So finally we have the executable file. So if we copy to the memory, this is called load. And the load time, and also as we discussed before, we can use a shared library, dynamic linking, or DLL file in Windows programming. So such as the DLL or the system library will be connected so during the load. So at this time, the address will be finalized for the addresses. So this is so we have the different type of address. The first, the symbol address is in our source code level. So source code level address is like the integer I. We do not use the memory address or offset to access the data. Instead, just the integer I or the file and so on. But this one will be compiled and the specific location, like the integer is a 4 byte from the 000 and the 14 bytes for the blah blah. So it's a logical address. It's a relative address. Okay, after compile. While after is link to the not link, load to the memory, it's an execution. Finally, it has the physical address. It's absolute address you will get. By combining one, base plus the relative address, logical address. So like this. So this is the comparison between the logical address and the physical address. Okay. Any questions so far? We have 5 more minutes. So that, which means we have the two different type of address. One is the logical, another one is physical. Which means it's a relative address, it's a physical absolute address. Always we need to compare or the translate from the logical to physical or relative to the physical. Why don't we have the something comparison table between logical and the physical? Then we can reduce the computation, right? Instead of calculating every time, we have the comparison table. That is the memory management unit, MMU. So, like this one, 0 is 500. 500 is a, so we have the comparison table. Somebody may be curious, why not calculating every time? That will be simple, but it's the waste of CPU. So we need to calculate. So it's probably instruction level, so we need to, instead, why don't we have such a comparison table? However, this comparison table is called the memory management unit, so MMU. Which means this table will be accessed a lot, right? Whenever we process the instruction, we need to check this memory, the MMU. Then the current address is 500. That is physically the 20,000. Then we can access the 20,000 address. So which means we access a lot. So we need to put this table in the where? Very fast medium. Okay. So usually we put this memory management unit, the MMU, on the kernel, the memory space. Kernel memory space. Sometimes it can be in the cache, L2 or L4 cache area, L3 cache area. So we can keep the such a memory mapping table, address mapping table. Okay. Then we need to know where is that the table is. So if we put this table in the somewhere in our memory, we need to know where it is. Whenever we process the instruction, check this one, to check this one, this should be the address. So that address is in the relocation register. So which means when you access when you process the instruction, check the base and the limit. Before that, relocation register, then access the memory mapping table, memory management unit, then the base and the limit. So then finally we can process such a the data. MS-DOS use even the full relocation the register, which means we can manage a number of the memory management unit. So that is the memory management unit. Then actually, because it's already the math, okay, so we don't have to do the base and the limit check like as we have done before, like this one, if that is correct. So instead of using that, our hardware can be if we have the logical address, using the relocation register. So somewhere in our memory, then find the physical address. Then finally access the data in the memory. Okay. Dynamic loading is when we compile, then we can link a number of existing objects in the file system level. Okay, it's not the memory level. Then when we load into the memory, then if we have the shared library on the memory, like the .so file or DLL file, so that can be dynamically linked. Okay, it's during the load time. So that is called the dynamic loading. Okay. Benefit? We can save the memory. Okay. So, but we need to know where it is. With who is in charge of the operating system, the manage the structure, the dynamic loading. Okay, so let me stop here. We will continue the number of the functionality of the main memory management and the allocation in the next class. Next class will be Monday next week after Thanksgiving. Happy Thanksgiving. Enjoy the Black Friday. Nowadays it's nothing special for the Black Friday.
Cyber Monday.
Yes, it's already. Okay, happy Thanksgiving.